Hello, welcome to another episode of Xa Talk Show. Today we are going to do Advent of Code Day 7 in Wolfram language, live coding, okay? Live coding and Day 7, the problem is a bit difficult, I heard. So we are just going to focus on it and try to get it to get the solution, okay? Wolfram language, let's begin. If you don't know, I have Wolfram language tutorial just on my website. Just search for Xali Wolfram language complete tutorial. So let's start the Wolfram language engine. Okay, let's magnify. Sorry. Okay, so there it is. So yeah, let's begin. Wolfram language, and this is Expose keyboard. One of my favorite, my top 3 favorite. Okay, Expose keyboard. You can find reviews on xali.info. Go there, click the search, and you'll find it. Almost everything I talk about, the Emacs, my mod, whatever, you can find on xali.info. Okay, let's begin. So let's begin the Advent of Code, problem 7. Let me show you what's the problem. Okay, let's start a Wolfram language code and let's begin coding here. So this problem, day 7, basically I already read it. So basically you are given this is your input, a string, which is basically like Unix directory list. Okay, so for example, let's start PowerShell. Actually, I'm gonna try to go fast and less of random talk. For example, you can, I don't want Emacs temp. So, for example, let's start PowerShell. Turn this off and magnify this. So, for example, you can say ls. That's a Unix directory, Unix command ls. Okay. That lists all directories, and you can cd ... to go up one directory, and you can do ls again, so list directories, or you can cd to Xa Talk Show. Okay, so what is the directory name? Let's see. Talk Show. Okay, no Xa, cd Talk Show. Go into a directory and you can list. Okay, so so the input is this string. Let's copy it. Okay, that's like the Unix prompt, Unix command prompt. So today's talk show here. So let's put it down. Okay, in Emacs, so we can easily see it. So you are giving this input. Essentially, you want to build a tree. You want to generate the directory structure from this input. Okay, so let's start to code it actually. So let's go to Wolfram language. X input equals to a directory. So first thing you want to do is split the string. Okay, split the string. Okay, so string split. Okay, split by the input and split by a new line character. Okay, so once you split it, let's say x1 equals to equal sign is always problematic to type. Maybe I need to remap the keys. I have this abbrev EQ or EQQ. And I used to have a brief for typing equal, but I removed it. Anyway, so here's the input. Okay, you split it, and so every line that start with the $sign is the input. So let's think about how do you do this. So given this input, you want to generate the directory, a tree structure. You want to build a tree structure. Okay, and let's write it out. Given this input, build a tree structure. Okay, and this input, those starting with $, means it's a command. Okay, this is important. And so once you see a $sign in front, that means it's a command. Okay, and the possible commands are cdls. Okay, let's see cdls cd. Okay, so it's something like this. Let's do it properly. cd name. Okay, that's one case. And let's do it here. Then ls don't have a name. Okay, so let's see. Okay, so cd, these matching lines, cd something, and so there cd name or cd slash, that's a special case. Okay, slash means root. Then you have ls cd name, ls cd, and you have this special case. Okay, that means go up one directory. Okay, that's it. So that's the possible command names. Okay, showing browser, there it is. Okay, so then then you have the output. So anything else is the output. So let's let's analyze to see what type of the output lines are. Okay, so that's how I go about solving this problem. So let's narrow to region. These matching lines include a $sign. Okay, do it again. These matching lines $. Okay, and remove those lines. Okay, delete matching lines. Okay, so here is a possible output. We analyze, to see what type of it is. Okay, so the possible case is the name. Then number name. Okay, they are all separated by a space. Yes. Okay, the name, number, name. Okay, number, name. Wait, what is this? I584. Okay, what? LS584. I is a file. Let's see. HI. Yeah, so I is just a file. Okay, so so number number. Let's put the file name. Let's put the D name. Okay, so file name. Yeah, that's the possible output. Okay, now let's expand our buffer. Okay, let's make these what? Yeah, we deleted everything in front by mistake. What? Oh, we forgot. We didn't expand correctly, so now it's back. Okay. So possible output lines, that's these two. Okay, and yeah, so let's show in browser. So that's what we have now. Okay, so we got this input. Okay, let's magnify. The browser font size is probably too small. Okay, so now it's better. So video check, audio check. If you are here, say hi. Okay. Yeah. So let's video check, audio check. Okay. So that's the input, and possible commands are these types. So whenever you see these. Okay, so why don't we add a $sign in front? Let's see. Yeah, so there is a $sign. Okay. Hello, secondary account. Okay, so possible commands, then possible output, either the name or number name, okay? And so you start to read, you split the line, and basically you want to do a loop. You want to loop through the lines. Now, loop is typically a procedural style programming, but in Wolfram language, is you do functional. So let's see what can we do. Okay, so you go through for each time you see a $sign, it's one of these possible cases. And is it true that you always begin with a CD/? That's important because that's a root, So let's see the puzzle input. Okay, yeah. So you begin with that. That's almost a given, implicit given. So let's write that down here. So let's day 6. Yeah, today is day 7. So let's write down here. Okay. Save it, paste it. Window code day 7 input. Okay. So now that's today's day 7 input. Yeah. So let's see. 1,000 lines. Okay. So you always start with the root. Let's look at how because they are basically traversal directory. So implicit is that the first line is always that you start with the root. Then I assume it's also another implicit case that you cd to every directory for the problem. Yeah, obviously, because the directory you don't cd to, doesn't matter. And your goal is to construct this tree in some kind of data structure, and the actual required answer is that you want to find all directories whose size is less or equals to 100K total size. Okay, total size including subdirectories. Directories themselves are 0 size. So you count the file size in a directory and or its subdirectories. So if it's less than 100K, then you calculate the sum of their total sizes. Okay. So that means, given a directory, you may have lots of subdirectories that is less than 100K, but basically you want to find their parents, the topmost parents that is less than 100K. Okay. The wording is not phrased in a very precise way, To begin, find all the directories with a total size at most that means less or equals to that. Then calculate the sum of their total sizes. You see, this is ambiguous. So for each directory, it comes with a size, okay? But when you say you calculate the sum, does that mean, for example, this directory A, let's say it's less than that size? But let's say, then obviously all the subdirectories below A is also less than 100K. So does that mean you just sum A itself, the size of A, or do you sum A plus, its subdirectory? So I find this is ambiguous statement. In the example above, these directories are A and E, okay, and the sum of their total size is that. As in example, this process can count files more than once, okay? The sum A and E, the sum of their total size, A and E. Yeah, so, so actually it wants you to count including all subdirectories. So if this file, yeah, so the directory E only have one single file, and this file is less than 100K, of course. So you would count E and you would count A as well, and you sum the size of A and E. So, and the sum of their total, okay? And this process can count files more than once. Idiotic. So find all the directories with the total size at most 100K. What is the sum of total sizes of those directories? And this means you repeatedly count subdirectories. So it's not a good question because it's unrealistic, because the description says you want to remove, the disk size is full. You want to remove supposedly big files. So anyway, so first of all, still we need to build a tree, okay? So let's see, what is this? Input, remove, delete that. So go back to the code. So you build a tree, then let's see, whenever you see a list, so you must have a intermediate variable of current okay, something like that. Okay, whenever you see that, let's just write up some notes. Let's say that. Okay, then let's see the structure. Then after CD, it's almost always ls. Is that true? Let's see. Okay, so after CD, it's almost always ls. Let's check. That's true. That's true. Oh, wait. That's not necessarily true. CD. So after CD, it may be another CD. Then if the end of the sequence of a CD is an LS. Is that true? Yes. Okay. CD, LS, CD, CD, yeah, so there is always LS. So let's highlight the LS to be green. Power of Emax. Okay, pink. So now it's easier to see. This, yes, 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 yes. Yeah, so after CD, the last CD, there's always LS. Okay, go back. After the last CD, then there's an LS. Okay. So, okay, so that's basically that. Okay, so whenever you start to see LS, then you have either two possible lines. Okay, so you have two possible lines. Okay, then after that, then again it's CD and LS. Okay, so okay, that completes the analysis of the input. Okay, now let's see what we're gonna do. So we start with a CD, then so we want to build a tree. Okay, and what does this tree? This tree, each node of the tree has a name. That's a directory name. Okay, and so this tree, each node has a name. That's important because you need to put this somewhere. So this is a common problem when you build a tree, whether each node has information attached or not. So in this case, yes, each node has a name, and each node also has a size. Okay, let's write it down. Okay, each node leaf. Okay, and each leaf node has a name and the size. Okay, so okay, so then this is idiotic presentation because you see it uses a dash to signify an item, a node. Okay, anyway, so each leaf, so we are thinking about how to build a tree. Each leaf node has a name and size, so we need to store that somewhere. So what kind of structure we want to use a tree? So each tree, let's say in Wolfram language, so a node name size, node meta info. Okay, name and size, and also type maybe. So node name size type. Okay, so how do you Okay, you can do this as either key value pairs, a nested list of key value pairs, such as Python dictionary or JavaScript object. In Wolfram language, you have associations. Okay, so association, which is key value pairs. Okay, so list, association, where is it? Advanced graphics, pattern matching, functions, data structure, association, there. Okay, so how do you want the tree structure? Or more common is just a nested list of lists. So let's write them out. So suppose the first element of the list is meta info. Okay, then the second element is whatever. The first element of the list is the meta info. Yeah, I think I prefer it this way. Maybe not. Let's see. So the first element of the tree. So for example, let's write it out. Okay, so two ways to represent a tree. How do we want to represent the tree? Two major ways. Okay, a dictionary or a nested list. Where first item is meta info. Now, if you use a dictionary, which is a key value pairs, how do you represent meta info in a key? Yeah, that's a problem too. So I don't think I want to use that. I want to use nested list. Okay. So the meta info is a list. For example, there, name size type. Okay. So for example, we have name, size, type, the. Okay, so meta info is a list, and meta info is a list, name, size, type, okay. Type is one of the file, okay, a string. So that's an example, and here is another example. Okay, and a file doesn't have any other things. Okay, so yeah, so this is not looks like that. children is a list of nodes. Okay. For each node, the first item is okay. So this is meta info. For each node, the first item is meta info. Okay, that's essentially that's a spec of our tree. Okay, yeah. Okay, yeah, that's our tree structure we want. Now, okay, now let's write the code. Now let's put this into talk show. Okay, so now let's go back to the code. Okay, now let's start to read it. Okay, once we split, oh, this is gonna take a while, 30 minutes already. Hello, Laser, Lassie, Kleiman. Okay, so now let's start to read. Let's build a tree then. Okay, so we want to process each line, one line at a time. So we can use a map or a do loop. Let's see. Let's write out the algorithm. If it's a command, okay, if it's a command, what type of commands are there? So if it's a command, cd or ls, so there's always cd first. Set current and oh god, this is gonna be, let's think about this. Set the current, so we don't have the size information ready, but we do have the meta info, the name, and size is not ready, and we do have a type. So each time we can start to build a each time we can start to build a meta info about the node. So let's look at the input. So cd / so you can build the meta info but without size. Okay, then you ls is the children of that node. Okay, yeah, cd is always, the last cd is always followed by ls. So once you got the ls, you got the children of that node. Okay, then you cd again, you cd to a Okay, so you can, so let's see. So now you have an issue, or maybe you don't, of building a tree bottom up or top down. So top down approach would be, you can just get all the CDs first so that you know all the directory names. And you can also get all file names and their size first, okay? So this is not sequential, but you get all the directory names, then you get all file names and their size. Then you look at so you still need to know what's the current directory whenever you do ls. Okay, so that approach is not good, probably. It's probably better to build a tree as you go. So maybe let's just start to do it. Okay, so cd, so if it's a directory, so you cd to a directory, then you eventually do a ls, then you got the children, their children, and that children needs to be added. So let's mark build, okay? So first of all, cd ls, so you got the meta info. Let's just say meta, okay? So meta equals to slash size, we don't know. We can leave it nil or something. Then type, okay? Okay, so we got that. Then when you see ls, children of last kunde, okay? Pseudocode, okay? Pseudocode. Let's say the pseudocode. Okay, then when you see ls, add all lines to the children of last kunde. How do you do that? So kunde, so to begin, so you do that, then append meta to, prepend meta to tree. No, that wouldn't. So temp the tree. Okay, so global tree. The tree, kunde tree, okay, kunde tree, meta, okay, then prepend, that's how you build, okay. Well, yeah, so then when you see ls, append all to children of kunde tree, something like that. something like that. So yeah, so let's start with the global tree. Okay, then so let's start the loop. How do you want to do the loop? Okay, let's see, let's go back to so we want to map to a list. Okay, so you look for map function to a list. You can use map or scan. Map returns a list, just like other languages. Scan does not return anything. Okay, otherwise it's the same. So we can use scan. Are there a better way? Okay, I mean, are there a better approach to build this tree? Oh God, this problem is gonna take 2 hours. So if we use map or scan, that means we have to write a function. And what the function will do, it's not going to be a functional programming function, but rather it's going to be the function is going to be a procedure of doing these things. So okay, so okay, sorry, I have to think about this. So you can use map or scan. If we do it this way, yeah, we map or scan. If we do it this way, it's procedural. Or okay, so map or scan. So the function needs to do a bunch of things. Okay, so let's start to write some more pseudocode. More pseudocode, possible commands, possible output. Okay, let's start to write code. If line equals to if the first character of the line let's see if that works. Okay, so you cannot use that for string. You need to use string parts. Okay. Okay, string start queue. Okay, let's do that. If equals to $, then it's a command, otherwise something else. Okay, and what kind of command are there? CD and ls. Okay, So now CD or LS. Okay, it's either CD or it's either LS. Okay, now if it's CD, okay. So we got nesting. So let's do switch statement. Okay, let's do switch or which. That will give you cleaner code. Okay, switch or which. So this is a condition. So condition, you go to Boolean conditional, which or switch. There are two inputs. Okay, test expression form. Oh yeah, so switch, you start with a value, then after that comes with many pairs, then you compare the value to each of the key of the pair, while which is just a list of pairs. Each pair tests a condition, so that's what we want. So which. Okay, so A, B, so these are pairs. Okay, things like that. So the first one is okay, so actually, so we can do it this way. Okay, so again, how many types are there? CD or LS. Okay, so if it's a CD, then what do you do? So when you see a CD, you need the temp direct. You need a temp temp variable. Okay, let's use a temp variable. Okay, so it's like that. Temp variable. The temp variable is gonna be not info. Okay, not info current. Okay, then and maybe current tree. Not info current tree. Let's put size there, whatever that. Okay, so if it's a CD, yeah. The name. Okay, so now you need not name. Okay, so actually you need a line. That's the current line. So if X line, that's already there. So if the line is that, maybe you can split the line first. Okay, so what are the possible? Yeah, very simple. 2 items or 3. Wait. Okay, line info. So we can just say okay, so CD or LS, okay, CD or LS. So if it's a CD, there's always three items. So not name equals to three. Okay, and so that's one thing. So if it's a CD, let me just code it, okay? Hey man, how's it going? Going good. String start. Okay, string start with yeah, pattern. Okay, so if that is that, wait, that's not right. Okay. Okay, so not type. Let's clean them up, clean my stuff up, okay, as I go. So line info, split the line, okay, and not type equals to line info. Okay, if it start with the $, then it's the and so we have line parts, not type. So and otherwise if it's a command, otherwise it's a file size. Okay, so let's see. So name, when it's a command, the extra info is the name. Okay, so when it's a command, the extra info is always the. Okay, so the type is always a the, and you got a name. Otherwise, name. Okay, I'm getting more clear and clear, but this will take a while to code. How's it going, everyone? Let's see, where is my check? Yeah, still going. This is gonna take a long time. So let's focus. So if it's a command or it's an output, then when it's a command, so either it's a command or it's a output, and when it's a command, you have, so this part you need to do for sure. Then if it's a command, you have not name. Okay, so there are several issues. There's a not name. There is then ls you can almost ignore. It just signifies, yeah, ls you can almost totally ignore completely. So if it's and type, so maybe okay, so let's start to put stuff here. Fuck it. One, two, three. So $sign or not $sign. Okay. So yeah. This code is all wrong, but let me just code it, okay? So here it means it's a command. Then when it's command, you have a name and you have a name, okay? Except when it's ... okay? Yeah, there's a lot complicated things going on, so Okay, I'm gonna not talk too much. I'm just gonna focus on coding it. String starts with, if it start with $sign. If start with the $sign, then it's a command. Then there are two types. Then, okay, there are two types. Then, okay, maybe it's better to just okay, then process file. Okay, so if it's a command, then if the second part is CD, so if you can do that, you need to split the parts anyway. Yeah, doesn't matter which one it is, so you need to split the line into separate components. So that's why this thing is there first. Okay, this ignore for now. Okay, so now if the line, the second part is equals to CD, okay, so if it's a CD, the second part, so it's CD or LS. Okay, now if it's LS, okay, but if it's a CD, then you have the third component. Okay, the third component, that is the name. Okay, the name. So let's put the name. So if it is a command, then the second part is CD, then you have a the name, except it's ... Fucking Unix, fuck. Okay, so you actually maybe, so it's a CD, and if the third one is not equals to ... then the name equals to that. But every time you do CD, you have to change the too. Fuck. You have to change the current so if the third part is not that, then okay, hold on a second, then you have that, and God, you need to build a current. You need to, so current is a string, so basically you need to append the current name into that current string. God, this is gonna take another hour at least, I think. I want to take a break and stuff. Shit. Okay, let's look at this problem again. Is there some easy way? So, it shouldn't be too difficult, but actually it is not trivial. I mean, it's trivial this is like real world coding. I mean, it's trivial in a computer science sense, but to actually code this, I wonder if the chat GPT can just spit out a solution, a program. So let me think, are there other ways to do this? So one way you can get all the names and then you look at the last changed to directory, then you add their children. So the first scan, one way is to do multiple scans of the input. So the first scan will get all the directory names. Then the second scan will get all the file names and file size. Okay, this is kind of logically simple. Once you get so you have a table of the names, you have a table of file sizes. Okay, then you do another scan where you scan for the last CD statement, the last CD statement, this one. And then, so you get the last CD statement, and basically then it's followed by ls, then you get in between the file things, a bunch of files. So that would first scan, get all directory names. Second scan, get all file names and their size. Third scan is actually to build the structure. So for every last CD, so all the sequences, every chunk of sequence of CD is to obtain, the critical part is to obtain the current directory, okay? The current directory. So you need to pass this ... into the path. Okay, once you get the path, you can... Okay, there are so many ways to do this. You see, so for this example, these files are children of the directory D. Okay, so how do you build the tree? So if you already have a tree so far, you need to add these children to that particular node, which is not easy because you already have a tree structure. Then you need to find the position, add this to that node. So that's one way. The other way is to simply build a list of all directory paths. That would be easy. Yeah, that would be easy. So just like in the let me show you. Okay, just like the Unix. So what you do is you so you have cd so recurse filter HTML What? Yeah, do it. Okay, so actually cancel. This is no. So what you want to do? Fuck. What you want to do is that, then this is PowerShell. Yes, this is what you want. You want to build a string like that. Okay, once you got this list of strings, then you need to turn this into a tree. Hello, Huang. So which way to go? So we can build a tree as we go, or we build a list of paths as we go. Once we got a list of paths, then we turn this list of paths into a tree. Okay, the problem actually requires file size, summation of files. Fucking problem. This is not as simple. So, okay, so you get so even if you get a list of file path like that, you want to turn this into a tree structure, and that is actually a problem by itself. Yeah, so is there an easy way? Is there an easy way where you just got the list of file paths and turn it into a tree structure? No, there's no easy way. No. So instead of doing that, you actually want to build a tree just by each step. Okay, so we back to here. So you want to build a tree in each step. I'm sorry, I just have to think about this. You cannot just start to code it. I really just need to think about this. So each time you encounter, so actually we are on the right track. It's just very tedious and lots of thinking. So if it's a command, then if it's a CD, then you want to update the current path and stuff. Okay, so if it's a CD, then you got then okay, what is a current? Current begin with a slash. I mean, in the beginning you get a slash, so update the current. Okay, but the current is actually supposed to be a position in a tree. Okay, this is not so good. This problem, you're just gonna see me struggle, and let's see, 3 people, 2 people. Not so good. This is not fun. I'm probably just going to be mumbling for the next hour, like right now what I'm doing. So I'm thinking actually just chicken out, stop the video, and I will for sure get it to work offline. Then, but if I do that, that then that loses the point of me doing this live. Then this video is wasted. Okay. I will not stop. I should just continue. But okay, I should just continue. So you want the current directory, so I have to think. I just have to think about it. Okay, actually, let me take a break, okay? Okay, I'll be back in 5 minutes. Yeah. When the whole thing is done, it's going to be one single line. I'm gonna tell you. Yeah. But okay, be back in 5 minutes. back. So we can build a tree as we read the list. Another way is we build the list of file path like that, then turn that into a tree. Now I wonder if Wolfram language has a built-in functionality to turn this list of path into a tree. So let's look at that, because that would be an interesting feature of Wolfram language. Okay, so let's look into, maybe there's a feature of doing that. Another way is that we don't build a tree at all. Instead, we get this list of file path, and for each list, for each item, for each path, we make it a pair, which is the file path and the size. So if it's a file, then you have a size, and if it's a directory, let's see, do we have a we don't have a directory, so filter. So if we don't filter, then we get all sort of for example, let's cd to Emacs, okay, because otherwise it's huge. Let's cd to Emacs. Let's cd to, okay, let's do it there. So now if we list the directory, you can see some of them is a directory name. You see, this is a directory name, and a bunch of files, and some of them are directory names, such as these. So if we get a list of file path like that, and then for each item, for each file, we add a file size, like make it a pair, and also for the directory, we make it a pair. Then we got the size, because the problem asks for computing the size, basically. So this is one approach. Get a list of path and add a file size to each item. Then we can compute the directory size by the files in that directory. Once we have that, so it's possible. Is it possible to turn this list of path into a tree in Wolfram language using some built-in functionality? Maybe, because Wolfram language has a lot of tree functions, graph and network. Okay, so let's see where they are. This feature is kind of new, since year 2000. So I never used this computation on graph and network overview. Okay, let's look at that. So you have graph object with vertex and edge properties, graph data, okay, complete graph, okay, random graph, adjacent graph, highlight graph, okay, graph object with vertex and edge properties. So if you want to represent the directory structure as a graph, then okay, edge, let's see. Okay, so this is how you represent a triangle, a graph. A graph is a generalized tree. Tree is a special case of graph. Tree is defined as a graph such that there is no loop. They don't come back. So tree is a special case of graph. And in the Wolfram language, graph function, this is a data structure that represents a graph, any graph. So if you want to use this to represent a directory structure, then the edges, each element is an edge of the graph. So you would have, for example, directory. So each edge is 2 elements. Each element represents a node. So if we're going to use this as a directory structure, then the nodes will be on the left side. It's always a directory. So in that case, it might be a string of the directory name. Okay, so on the left side is a string of a directory name. On the right side, it's again a string. It's again a string. It might be a directory or it might be a file. Okay, so for each element is a string to string. Okay, so this is how you can represent a graph. Now to use this, we are thinking of the possibility of using this to solve our problem. So if we use this, but we also need to represent the size, and so for each node you need a meta info, right? So each node will be a name, either directory or file, but you also need a meta info to indicate that it's a directory or a file. So if we use this on the left side or the right side, it's going to be a pair. So on the left side, for example, it's going to be a string directory name, but also a size. On the right side, it's a directory name or file name and with a size. So it's a list of pairs. And you can do that. Okay, so that's one way to do, if we want to use this. But what is the advantage of using this? I don't know, because it can get very complicated. Graph and network. Is there a way to we are trying to see whether it's suitable to exploit this Wolfram language graph data structure to make our solution easier. Okay, so you can highlight elements in a graph. So given a graph, you highlight the nodes, that can be vertices, edges, or subgraph of G. Okay, so basically this allows you to visually represent the tree. Okay, that's not what we want. It's not useful to us. So we can represent a graph. Then this graph data, curated collection of theoretical empirical graph. Okay, that's like cities and stuff. Cities or Earth data. Let's see what does it do. Oh God, he's huge. Yeah. So we need, let's go down. Okay, graph data. Yeah, so this is a theoretical graph. You can just give a name of a graph, a known named graph, then it just creates the data for you and you can visualize it. Okay, so that's what this graph data does. Okay, that's not useful to us. So you can represent the graph. You can generate a graph by a given graph name. Then you can highlight graph. Then you can plot graph. Properties and measurement, graph distance, shortest path. Okay, no, these are not useful for us. So this is mostly graph theory. Yeah, that's not useful to us. Boolean computation. Yeah, so okay, we don't want to use graph. Now, is there some kind of function related to directory structure? That I don't think so. There are, but it's just like typical programming language where you can get file size, the size, total the size, and things like that. Where would that be? That would be data manipulation, time-related engineering computation, recent features, scientific. Okay, it's not. Okay, so you go here, language overview. There are 6,000 functions, so it's not here. So instead, you want to search for file, okay, directory. So there's tons of functions related to directory. Directories and directory operations, okay? Let's go there. Yeah, but I don't think it's helpful for us because these are just like typical programming language. Directory, set directory, this is like current kernel directory, set directory, okay? Then you can get parent directory, directory name. So how does this work? Parent directory gives the parent of the current working directory. Oh, okay. So parent directory gives the parent of directory . Okay, this is useful. This is when you have a path. Basically, it just returns the directory part. Okay, so just like typical other languages. Let's see. Yeah. So they may be useful operations on file names, directory, and directory operation. Construct a file path programmatically. Okay, that's not interesting. That's just construct a file path. Okay, so not useful to us. So let's go back. File name join, split. Yeah, so all these not useful. Because our problem is not really about manipulation directories. It's really about building a tree. So, okay, so that made us think of another way to solve this problem. So when you do this, you can actually create a file of that on your file system. This is very interesting. You create a file. So you use your file system to create this directory structure. And for each particular size file, you actually create that file. But that's not good. That's one way to do it. But you actually create a bunch of files. That's not efficient. That's kind of going around the problem. The problem really is to build a tree. Okay, so again, there are several ways. So you can build a file path. Then you add the file size for each. So then your problem becomes working with a list of paths, which you can do, but it's not efficient. Okay, that's again like going around the problem. Yeah, you can get a list of files. File path with their size. Then you can find the directory's total size. Yeah, you can do that. But it will be inefficient and also kind of going around the problem. The proper solution is truly you need to build a tree. You need to build a tree that represents this input. Okay, so let's go back to, I think at this point we go back to truly we just need to build a tree. Let's not, try to go around the problem. So we need to build a tree, okay, which is not so easy, okay. So to build a tree, okay, we decided we want to do that. We actually have to build a tree. And also we decided the tree structure. Yes, we decided, so there are two possible ways. One is nested dictionary, nested key value pairs. But we reject that solution. We reject that representation of a tree using a nested key value pairs because for each node of the tree, may it be a directory or may it be a file, which is a leaf of the directory. For each node of the tree, we need meta info, such as the name and the size. So if you use key value pairs, typically the key would be the directory name or file name. But where do you put the size? So that's a problem. Unless the programming language allows you to, say, attach a property to the string or to the key, or you use a list of pairs as a key to your dictionary. But if you do that, that kind of, let's see. Okay, so you can use key value pairs to, so you can use a key value pair as the key of your tree. So each node, or the key of a dictionary, the key would be a pair, a name and the size. Okay, but the point is that you do have to use a pair for your key to represent a node. And what is the problem with that? Well, the problem with that is that your dictionary, your nested dictionary, is now not simple, because in vast majority use cases of a dictionary or hash table, your key is always a simple string, just a string or a symbol. But now you need the meta info of file name and size. So the size. So now your key is gonna be a pair. So we can do that because the Wolfram language, the Wolfram language association data structure, which is what Python would call dictionary, allows that. Your key can be arbitrary expression. Yeah, we can do that. Okay, so right now we are thinking about how to represent a tree, revisit this issue. So you can use association, or also known as associative list, also known as dictionary in Python, or known as hash table in Ruby or Perl, or also known as map in JavaScript and Java. Okay, so you can use these basically key value pairs to represent nested key value pairs to represent a tree. Okay, so that's one way. Another way is just pure nested list, where the first element is taken to be the meta info about. So we can do that. The first element would be the meta info. Okay, so in either case, so again we have two possibilities. Okay, we are thinking of which one to choose: a dictionary, a nested dictionary, or a nested list. Now, if we use the list, then the first element of any node will be the meta info, and it will be a name, size, and type, or file. The type we can actually skip, because the leaf nodes are files always. The files are always leaf nodes. So if it's not a leaf node, it's a directory. So we can actually skip this. We just need a name, meta info, a name, and size. Okay, is that right? Yes. Okay, so meta info, name, and size. Okay, so two ways: dictionary or nested dictionary, or nested list. Okay, Now let's think about which one is easier. Which one is easier? So the problem, given this, we have already decided that we want to go through each line one at a time, and as we go through, we are going to build a tree. We already decide on that. As opposed to scan this list multiple times, get the directory name first, get the file names and size first, then build a tree. Then, so we decided we're gonna just go through, and as we go through, we are going to build a tree. Is that possible? Yes. Okay. Now, so what does it involve? So each time when we start to do a ls, we get a children, and this is when we need to add these children to our tree, to the main tree. Okay, this is the birth of a new nodes, several nodes. So yeah, so when do we start to add a node? We begin with a empty tree. So we add a node when we first encounter a CD, and when we, so that's the question. When do we? So whenever you have a CD with a name, okay, whenever you have a CD with a name, that's when you add a new node. Okay, and whenever you have ls, that's when you have a new bunch of nodes, children nodes, to the current node. Okay. So we can, so this is, Okay, so the point here is that we need to add nodes in this process. We're gonna need, and it happens when, okay, so we are going to add a node. And how do we create a node? Well, when it's a CD name case, we build a node. So so we need to build a tree. So when you create a node, okay, then you need to attach this to a tree, to an existing tree that we have built already. Okay, and there is a problem of where or how you're gonna attach the tree, attach a new node to the tree. Okay, so let's look back to our two possible ways. One is association, a dictionary, a nested dictionary. The other one is nested list. So let's think about the association case first. So suppose you have a nested dictionary, and now you have a current directory with a bunch of children you want to add to your nested dictionary. Okay, how are you gonna do that? Well, what you need is you need the actual position of the nested dictionary to add to. In other words, you need a specific way to, so you need a bunch of key names in a specific order that indicates how they are nested. Then then you create a new dictionary under that dictionary. You insert a new dictionary into that dictionary. So if you use the dictionary or association, you need, let me explain. Okay, for example, let's say Python. So let's go to Python. So for example, Python, you use a dictionary, right? I'm using Python to explain it because that way people understand. Because Wolfram language is, probably new to you guys. So association, you get key, get value, or delete key, or add key. For example, this is how you add a new key into an association. But in Python, let's go to dictionary: string, arithmetics, Boolean, conditional, loop, data structure, iterators dictionary. Okay, so here's Python dictionary, but what we need is nested dictionary. So this is how you add a entry, add a key value pair to the dictionary. But that's a flat, that this is assuming you have a flat dictionary. So when you want to add a key to a nested dictionary, you need to get the position. So you need something like this. Okay, in Python, you need something like key 1. Like that. Okay, so so this key 1, 2, 3, you can call them indexes. So you need a sequence of index to add your key. Oh yeah, that makes sense. Now, so each of these key will just be directory names then. Okay, now it becomes so clear, much clearer than before. Yeah, each of these key will be your directory names. So when you go through this problem, each step you have a value of current directory, which is a path like that. So when you are ready to add a new node into your tree, so you start, you have the current directory, which is a path. Then each part of the directory name becomes a key. So this is how you can add. Okay, so yeah, okay, I think I got this is a very easy way to do it. Yeah, so let's use a association list or key value pairs. This is, because the key is just a directory names. Yeah, so this is an easy way to represent the tree, at least for the directory structure, using a nested dictionary. Okay, what about, now let's go back to the list, nested list. If we are using nested list, how we add a tree, how we add a new node? Well, in that case, you need the numerical indexes of your tree. So if you have a list, it will be something like this. Okay, list. It will be like that, something like that. Okay, if you are using a nested list to represent the structure. Okay, who is pinging me? Oh, Lazo, these people come here, watch my videos. How does it compare with Google in terms of quality results? These people, I have a lot of young people following me. Many of them are teenagers. So, hello, we have a gender selection box. Hello, Oflamio. No, we are working on a tree. Okay. So yeah. So now we have the two possible data structure: a dictionary, or we're gonna use a list. It looks like dictionary is better, because if you use a list, then there's no direct way of a given file path to the positions of a tree. That's right. So you need to keep a current value of the indexes. And that's tedious. That's very tedious. Okay. So we don't want to use that. Okay, so we want to use the dictionary to represent a tree, where each node is a key and it's a string. Okay, but now back to another question. How do you represent the meta info? For example, so if the key is a directory name, but how do you represent size? Well, in that case, we can create a separate list to represent the size. That's right. Okay, yeah, we can create a separate, lookup table to represent where given a file path, we can represent, we have a value of its size. Yeah. Okay, so we decided nested tree, two ways to represent the tree: nested dictionary or nested list. If we use dict, then it's easy to represent the position we want to add a new node. And that's just a list of keys or the names, okay, like that. But if we use a list, then we need a list of position corresponding to the current, okay, like this. This is hard because we need to maintain how the names corresponds to the indexes. Okay, so so this is a problem of ways to represent a tree. So far we decided we're gonna represent by a nested dictionary. Okay, let's write it down here. Actually, let's just put it here so we have all the information about how to solve this problem. Okay, here. Okay, now close that, reopen, back to the Wolfram language code. Okay, so now we decided with clarity that we want to represent a tree using a nested dictionary. Okay, yeah. Now there's problems of storing the meta info, such as name, file order name, and the size. Okay, when using a nested dict to represent we can have a separate list, separate dictionary, where keys are file path, okay, and value is size. This way we can easily find any nod's size. That's right, that's how we solve this problem. So finally we decided we're gonna use a nested dictionary to represent the tree, and the problem of how to store the meta info corresponding to each node is solved by using another dictionary. Okay, good. Now we have clarity instead of a blind, instead of a trial and error. Okay, so now we're gonna use a nested dictionary, and now so a lot of info here we need to redo. It doesn't. Okay, now let's back to. I'm gonna solve this problem in this video for sure. Nobody is watching. I think 2 people. Who are you? Okay, so use the dictionary. Okay, use the dictionary. Okay, now let's go back. Let's go back to our code. Okay, so here's the input. Split the input into that. Then we process each line one at a time. And build a tree as we go. Okay, we decided this is the optimal. Instead of scanning the list multiple times, one time to build all the names, another time to build all file names, then build all path, then build a tree from list of path. Okay, that's one way to go, but we decided that's not. Oh, actually now that way also can work out, because now this is how you add to the dictionary. So now it's easy. Once you have a list of file paths, it's actually quite easy to turn them into a nested dictionary that represents the same structure. Because each part of the path is just a key. That's right. Fantastic. So which way to go? So should we build a list of file path first, or should we directly build the tree as we go? Let me think about it. Okay, so if we have a list, let's look at the file path again. So if we have a list of file path, can you actually build a nested dictionary easily? Yes. Okay, WolframLang says build a list of file path first. Okay, I'll take your suggestion, because the other way, optimize later. Okay, good. I'll take that. Fantastic. Optimize. That's a good. That's a good advice. Let's finish the problem first. Okay. So we build a path. We build a list of path first. Okay. Okay, so then turn the paths into a tree. Okay, fantastic. And this comment, let's just forget about it. Okay, let's do that. Okay, now start to get into the details. So if it's a command, then we need to several things we need to do. Okay, first of all, global tree. Now we know it's a association now, not the list anymore. So it's gonna be an empty association. Yeah. Okay. Let's start to. Oh wait. So we don't worry. Let's not worry about that first, because we are going to build a list of path first. Okay. Okay, that's what we're gonna build. A list of strings. Okay, start with empty. Now let's get to starting to get okay, so let's see, what is it? If it's a command, set current directory. Okay, so this let's those are things we were thinking before, but let's start fresh. Okay, so start with a path list that's empty, and we split the lines. Okay, so x1 is lines. Okay, let's rename them so it's better. Okay, lines. So each one of these is one of that. Then you need to map. Okay, map to the lines, and you map this function to the lines at level 1. Okay. So line parts. So now this is a list of line parts list. Each one is like, let me show you. Okay, for example, each one is going to be like okay. Okay, I'm going extra miles to, because okay, so anyway, so people can understand. So now we have each line part list, and actually let's run it. So actually we have a example. Let's run it. I mean, so you can actually see so far there. Okay, yeah, so this is line part list, list of it like that. Okay. So next we're going to we're gonna go through this line part list. Okay, now it's more clear. Okay, so now we want to map again. Okay, map to this list and first level. Okay, and we need to map a function to this list. Okay, and this function will be okay, actually this is going to start to process it. This is not, yeah, this is starting to actually build the file path. Okay, yeah, we can still do one function, but it's gonna be a big function. Okay, let's just say result. and it's not, yeah, let's do it, yeah. So so what is going to be, so let's forget about that. Let's we need some things here. Okay, so let's get okay, let's start here. So it's going to be a function. Okay, now the function, let's write it out for okay, function something expression. Okay, the input is just line parts. Okay, what? Okay, and what does it do? Here is a body. Okay, so the body is gonna be a bunch of if statements. Okay, we're gonna prettify the code. Hold on a second. So let's, you know, in Wolfram language you can prettify the code. Fantastic. Okay, so now, so line parts, right? We're gonna map this function and map it to this list. Okay, now a function. Okay, now what does the function do? So it's a bunch of if statements. Okay, a very bunch of if statements. So first of all, if it is a, if the line parts, let's not just say line parts, let's say line. Okay, bear with me, it's simpler. Actually, it should be line list. Should be line parts. Okay, it's just SXX. Okay, fuck it. Okay, so if, okay, now if string, let's not do that. So now let's say, so if XX, the first part is equals to a $sign, okay, that means it's a command. Okay, okay, so if the first part is a $sign, so we see, we analyzed here before, if it's a $sign, then it's a command. Then we need, then what we do is, so it's a command. Then if it's a, where is this? Nested if expression. Nested if expression. Fucking confusing. So if it's a command, let's see. Oh, here. Wait, where does it end? Yeah, here. Okay, so if it's a command, then here is line is not a command. Okay, so here is what happens when it's not a command. So here is what is a command. Okay, so if it's a command, then we do if it's a CD. Right? Yeah. So if it's a CD, then what we do, yeah, if it's a CD, 1 2 3 1 2 3 1 2. Okay, so anyway, so if it's a command, then there are two possibilities. It's cd or ls. Okay. Okay, something like that. So if it's a cd, then what to do? Well, we have a name. We not necessarily we have fucking shit. So we have cd name or dot. Okay, cd. So there are two possible cases: a name or dot. So if it's a cd, okay, let's think. So what are we gonna do? So name. So once you get a name, you want to append to the current directory. I mean, we are building a file path. Okay. Yeah. So cd a name, append the current directory, and if it's a dot, then remove the last directory. Okay. So yeah. So okay. So cd. So if it's a cd, then there is two possibilities. What the fuck is, where is this connected? If it's a cd, then we build the path. Okay. Now let's put this here temporarily to make here clear. Okay, so if it's a cd, then we build the path. Now let's create a current path. Okay, let's create a temp variable. Let's say, okay, empty. Okay, current path. So if it's a cd, we and okay, so something like that. Okay. So if it's a cd and depends on its dot or not. So if third element is equals to dot, okay, then that means take off the last actually this should be a list. Let's make it, because list is easier to work with. Okay. Okay, list is easier to work with. Okay, begin with empty. Okay, so if it's dot, then drop the last element of the list. Okay. I'm pretty sure that's what drop -1. That means delete. That means delete last element. Okay, yeah. So if it's dot, means goes up one directory, so the current directory will just drop. But otherwise you want to append that with the third part. Okay, fantastic. We are going somewhere. After 2 hours of coding, we are going somewhere. 2 hours of analysis. Now we are like in the flow. Okay, and I can guarantee you the final solution is gonna be one single line, more elegant than any other in the universe. You look online, Rust solution, Golang solution, JavaScript, Python, Ruby, Bash, whatever language. This Wolfram language solution, I would say it'll be shortest in terms of the character count. I can shorten the function names later, but at least it's the shortest. It may not be the most efficient, but you cannot compare with C, but it will be the shortest. Including Haskell and Lisp. Okay, let's back to the code. Okay, so if the third part is ... then you drop the current list. Okay, you set the current to that. Otherwise, you set the current to that. And now there is a shortcut, because this, you see this line. Let me show you this here. You can actually improve it by, since you're gonna assign it anyway, so put the assignment here. Okay, so this line, it would be equivalent to this line. Functional programming. Okay, yeah. So current path, so CD, so if it's a CD, then you change the current directory. Okay, yeah, so double check, you need to double check, I need to double check. Instead of later on running the code, you don't know where it went wrong. So append, give the expression with element appended. That's right. Okay. Okay, we don't care about efficiency right now. I just want to finish the problem. Otherwise, I typically stuck for n hours in my videos. That's no good. Okay, so we got so what is going on now? So we processed, so after a bunch of CDs, we have the current directory path. That's right. Now the ls case. Okay, now it's the ls case. What do you do with ls? Well, wait, so and you need to do one more thing, my friend. One more thing. Once you got the current path, you need to push it to the to the current path list. Okay, push and shove. Push. Wait, what? Oh, okay, so wait. Oh, wait, so you need a, yeah, push here, path list. Okay, each element is a or file name, so you need to push to there. Okay, so path list. Okay, so push in Wolfram language, you don't have shit like push. Instead, you say the proper English, append, prepend. Okay, no push and pop. What the fuck does that mean? Can mean anything. Like I'm gonna push you. I'm gonna pop your cherry. It could be anything. But idiotic industrial programmers, they are used to this push and pop and where, such as in Haskell, where something, or in the SQL, something, where, Where is it? You know, confusing, ambiguous abuse of English. Push, pop, where, and let. You know, in Lisp you have let something. What let? What let? Let's go crazy. Let. Idiotic industrial names. Okay, and in C it's worse. Malloc and what the fuck. So proper English, append, prepend, okay, not push. Okay, append to this path list and append this thing. Okay. Yeah, append to. Okay, let's say append to. Yeah, you're gonna use append to, so that we don't have to assign it. Actually, let's assign. No, let's not, because yeah. Okay, let's just do this. Okay, so yeah, append to path list, current path list. Okay, yeah. So every time we encounter a CD, we append to, but only when it's not dot. Okay, we need to modify this part. So yeah, you need to modify this part, so put it here. So if that is that, then that. Otherwise you, okay, so now we need to, okay, so let's redo this. Okay, so then also do this. Okay, so if it's dot, do that. Otherwise you do this. Okay. Okay, does that make sense? Let's see. Yeah, I hope that makes sense. Code condemned 77. Hey, we are making progress to this problem. Day 7. Build a directory tree. Build a tree, actually. Nothing to do actually with directory, because it's not about file system. Rather, it's using the concept of file system to induce a problem of actually about building a tree. So this problem is about building a tree. It's not really about directories or files. Okay, and we are going to hit the heart of the problem, actually building a tree, not doing workaround of using path. We are building a file path list first, then we build a tree. Okay, so current directory path list equals to that. Okay, if it's dot. Otherwise, this statement needs to come after. So yeah, it needs to come here. Okay, so yeah. Okay, so we have appended to the path list. That's a major achievement. Basically, essentially, that's gonna be corresponding to adding a node. Okay, now what if the command is ls? Okay, if the command is ls, let's see. So command is cd, we do that, then we add it. Okay, if it's ls, we do nothing, not a thing. How do you do nothing? Null. Okay, in Wolfram language, null represents nothing. Okay, yeah, so we start to read the next line. Okay, now the next line, which is when a line is not a command. Okay, So what to do when the line is not a command? Children, of course. You're gonna start to add a bunch of children. Oh, okay, so shit, Jesus. Then, but each children has also a okay, so then you need another dictionary that's children's, list of children's. Okay, I mean, you know, the size, file size table. Size lookup. Okay, and this is going to equals to association, which is association list, okay, which is dictionary in Python speak. So in Python speak, it's called dictionary. In Wolfram language speak, it's called association. In Lisp speak, it's called associative list. Okay. So association key value pairs, that's right. So association there, empty, okay. Okay, that's size lookup table. Now, that's our, yeah, so that's our procedure, okay. Next, so what if it's ls? What you gonna do when you see an ls? Do nothing. Okay, next, when the line is not a command, what you gonna do? Well, we're gonna add to the current add it as child to current. That's what it's gonna do. So the current what? Wait, we are not building a tree yet, so we actually just add it to the lookup table. Okay. So add to the lookup table, then it's gonna be two parts. Okay, key and value. Value is the size, okay, and the key is gonna be the path. Okay, so what is the path? Well, the path is the it is the current path. So let's see. Let's group them so that we can actually have some easier syntactical unit to work with, because I can, you know, press one key and get the whole syntactical unit. Okay, so lookup size. So what is a key? Well, it's first of all, you have to create the current file path. So the current file path is gonna be, I mean, the file, right? So if it's a ls, wait, so if the line is not a command, it means size and file name. Okay, we add to that table. Okay, so it's size and file name. So how do you get the size and file name? Of course, you need to split it. Where is our split? XX. Okay, so XX1 is the size. Okay. Okay. 2 is file name. Okay, so what do? You first of all, so you want to, so file name is here. File name, you append to the current path list, right? That's right. You append to the current path list, and you also need to do that. Okay, so current path list, you append it, then you actually you don't want, no, wait, hold on a second. So let's write some temp variable. Okay, let's get this right. Okay, let me show you how to do it. I'm sorry if this is I'm babbling, but babbling is good for viewers because then you know what I'm doing. File size, that, okay, and file name, that. Okay, now it's easy to understand. Okay, so with this with expression, that means like Lisp's let. In this case, it's constant. Okay, so then you can move this inside. Okay, so now so append current path list. That's just a current. Okay, append the file name to it, which is here. Okay, then you append to the path list of that. Okay, so that. Yeah, so that's one thing you need to do. Actually, there's another thing you need to do. So let me actually, let's do it here. File path equals to that. Okay, now it's readable because we are using variables. So you add so we are encountering a line that is not a command, so which means it's two things, file size and file name. So we got the file size, we got the file name, and we need to get the file path, and the file path is of course that current with the file name added. Okay, then so after you get the file path, you need to append your file path to your global file list because it's a file. We are building a list of paths, right? Yeah. So we do that. Okay, so actually, wait, what is this? Yeah, so that's one thing to do. We add to the global file path list, and then we need to add, we need to add to the file size lookup table. Okay, how do you add an item to a dictionary, to a association, so let's look up, let me show you the association documentation. So you can add by association. Okay, and let's look at my tutorial because I have better understanding in a different style. So my tutorial, so you want to add a key value pair to a existing association. So let's see, add key. So that's all you have to do there. So that's association, and that's the key. My back hurts. I need to like take another break. God, I was hoping I was, today I didn't do any video of my mugshot, so you don't see me. So, but I'm stretching. I was thinking because I need to be really focused. That's why I don't include a headshot. So you focus on my keystrokes and stuff. But it turns out, this is gonna be 3 hours. But we getting close, okay? So association key value pair, this is how you add it. Okay, or you can use associate to. Okay, let's use associate to, because I don't like the the imperative shit. Okay, association variable is that, and now you just need a rule. So the way you write a rule is like that. Okay, let me show you this rule here. Okay, so the key, what is the key? Well, the key is the file path. Actually, should we turn that? So right now the file path is actually a list of strings. Each string is the directory name. So should we turn this actually into a giant string, or should we just so that's so the code is not readable right now. Let's see what you guys are saying. Condemned 77 says some short words what makes Wolfram special. I just found that Wolfram got interviewed by Tim Ferriss. I need to listen to it. Stephen Wolfram got interviewed by lots of people. For example, Lex Friedman, he has interviewed Stephen Wolfram at least twice. And if you search YouTube, you'll find quite a lot of interviews of Stephen Wolfram over the past 15 years on YouTube. So, and he also goes around to different universities to give a lecture. So you'll find a lot of his videos. And, if you have watched my video, I have also done quite a lot talking about the language, so I recommend, if you want to learn the language, I recommend you watch my videos. There are some, not many other YouTubers that teaches Wolfram language. But I would say, if you trust me, I'm one of the major source for teaching Wolfram language, because I've been coding it for 15 years plus, mostly in 1990s. Okay, so, but if you want to know more about Stephen Wolfram, the person, he's also a physicist, computer scientist. He wrote Wolfram language, and he's a founder of the field of cellular automata, which is kind of very interesting, especially for you guys programmers. Cellular automata, a giant book on the new kind of science. Let me show you. So, new kind. So I went through the book multiple times. It's a huge book. That's about 1,200 pages, something like that. Very heavy. So I went through. I read them since when it came out, 2003 or so. Yeah. So if you want to know about Stephen Wolfram, he's got his website and blog, so you can read them, or videos. If you want to learn about Wolfram language, you can start from my tutorial. Okay, so that's a digression. Let's get back to the code. Okay, so I hope that answers your question. I don't know who is Tim Ferriss actually. Who is Tim Ferriss? I'm starting to digress a lot. American author, entrepreneur, I hate that word. Angel investor, okay, yeah. Okay, maybe he's good. I don't really trust these type of people. The 4-hour work week, the 4-hour body, the 4-hour chef. No, okay. Okay, interesting, but I am not sure about that. Okay, so that's about Wolfram, okay? And Samuel says, I didn't notice you didn't go to face cam until you mentioned. Wolfram is also on YouTube, yes, indeed, but you wouldn't notice it because YouTube doesn't push up his videos often enough. Oh, Tim Ferriss is the 4-hour work week guy. I see. Okay, back to code. Because I'm a nerd, so and I'm a programming nerd, and I'm a nerd in general. So my main interest is also mathematics, artificial intelligence. That's and philosophy and some linguistics, But yeah, so these are my things that I have obsessed in my life. So I don't care much about those entrepreneurs, except Stephen Wolfram and Steve Jobs. These two person I admire, and also Elon Musk. Typically when you talk about these super rich people, I don't like them. I despise them. But these three persons is exceptional. They have a huge, I would say, huge influence in my life, and I personally highly respect them, and I can see I synchronize with their view from in different aspects. Steve Jobs, Stephen Wolfram, Elon Musk, these three persons, in different ways, I very much like their view, and I like what they did, what they have done, and I like how their integrity, that's one thing I pay attention the most, the integrity of the person. Does the person lie? Like most politicians, does the person like doing questionable things make a lot of money, like 4chan, Reddit, like Facebook, these people, are they what did they do? How are they, you look at their life's events, history, are they always something controversial? Okay, so anyway, these three persons I highly respect, I admire, I respect, and I also associate with the way a lot of the way they see the world. Okay, anyway, back to the code. Let's back to the code. Now the Elon Musk guy, of course, he's today the richest person, so you'll have a lot of different opinions about him, and a lot negative. But if you ask for my own personal judgment, of course I judge. I look into a lot. I carefully. I don't. It's very hard. It's almost impossible to get me to like someone. Okay, so when I say I like Elon Musk very much, you can be sure that at least I put a lot of effort to look into. And he's, Elon Musk is not paying me, so I got nothing to do with Elon Musk, but I find him just great. Okay, that's my opinion. Okay, so yeah, so if you anyway, that's right. Let's get back to code. Okay, Wolfram language. Okay, so we made a lot of progress. A little break, that's good for me. I need to take a break to ease my back. Okay, so this part, okay, let's finish this part. So when the command, let's go back to code. Let's put my mind back to code. So when the command is encountering a line of file, what you do is you get the file size, you get the file name, you get the file path, which is a list of directory names. Okay, then you append it to the global file list. That's right. Then you add an entry to the size lookup table. Okay, and the key would be the file path. Okay, so here the key should be a string, not file path. Wait, should it be string or file path? Let's leave it. Let's leave it to be a list of strings where each string is a directory. Okay, let's not do optimization now. Let's okay. So far so good. Let's look at our overall structure. This thing, this copy. Let's go back to Wolfram language. Let's see if did we screw up the syntax? No. This is a complete code, nice looking. Now if we can we do it that way? Yeah. Okay, back here, and let's put here. Let's see. Yeah, it's much more cleaner. Okay, now we're gonna delete this part. See, efficiency. Okay, so here, whoops. Okay, so now make a backup. Now what do we do next? Okay, so far we have covered when the line is not a command. Okay, we covered all cases already. When the line is a command, cd ls. When the line is not a command, we missed one part here. You see, when the line is not a command, you have the possibility of a duh. Okay, more things to do. Okay. Okay, so now we need a if statement. Shit, another if statement. Okay, so we need another if statement. God. So you can see this with if statement. What you're gonna test? Yeah, you're gonna test if the first part is a. You're gonna test if the first part is a number. No, you're gonna test the first part is a duh. Okay, so let's put the if statement inside. We can't because this file size. Okay, so we have to put the if statement here. So if the XX first part is equals to a duh, then it's a duh. Okay, then you just do whatever duh you have to do. Otherwise, that. Okay, so if it's duh, you do something there. Okay, yeah. Okay, so what happens if it's a duh? Okay, it should be simpler. If it's a duh, then we yeah, so let's do a with again. So okay, so if it's a duh, then the first part, the second part is the name. Okay, so the second part is the name. Okay, and this we don't need, and this we don't need. Okay, very easy. All we have is the name. So what you gonna do when you get the name? Well, you're gonna you're gonna add. So this associate we don't need. You need to add the name to you don't care actually. If it's a directory, what you gonna do with it? You don't care. Ignore it. Oh, yes. That's right. Because we can just ignore it. Because unless later on you cd to that then you maybe do something. Because if it's a and you don't cd to the That means you don't get files in it, so you can ignore it. So if it's a duh, we just ignore the fucking whole thing. Okay? No. So okay. So actually, let's our code is complete. Let's run it. For the rest we can like delete them now. Okay, delete. Do we actually need the things we were trying to yeah, so actually we don't need it. Just delete the fuck. It's meta and shit. Okay, delete the fuck. So now our code is just that. Okay, so now what if we run the code? Let's try it. Copy it back here, select all. Okay, paste. Please, no errors, please. Oh, fantastic. Wait, something is wrong. Okay, let's look up our let's look at our global path list. Let's see. Okay, so you can see we have some error there. So you see this is a list of path, but let me show. Yeah, yeah. Can we do that? Okay, so yeah, so we can. So that's our path list. There's some error because we added, so yeah, we added cd to the twice. Okay, but let's look at the current path list. Let's see what we got. Oh, we don't care about that actually because that's temporary. Now let's look, wait, let's make sure our name is one single R. Okay, now let's look up what's our size lookup table. Okay, size is incorrect. Oh yeah, it should be file size. Okay, so not size but file size. Copy all. Let's do it again. Paste it here. Eval. Okay, so what is the size lookup table? Okay, so we made some mistake that we have repeated the names in the path. Okay, we need to fix it. Fucking shit. So we have to fix. We somehow added the names twice. Does it always? And also we have the file name wrong because it should be an actual file name, not that. So yeah, so that's not good. Okay, where do we get the file name? File name, okay. File path. Now, where is file path defined? I'm getting tired. We're not gonna finish the problem. and I'm hungry. File name, this is idiotic. So file name, so line is not a command, it means it's a size in file name. Okay, add to size lookup table. Okay, yeah, so if it's a directory, ignore it. Okay, now but otherwise you have the file size, but first of all the path is wrong. Yeah, the path list. So let's fix the path list first. So our path list, okay, here, okay, so path list, God. Let's rename again. Let's rename our things. This is too long. Current. Okay. That makes our code much easier, simpler to see. Okay, and then our path list, let's just say paths. Okay, okay, each element is a okay, and so our x path is incorrect because if x3 equals to that, this nicely formatted thing is not semantic. So if x3 equals to dot dot, so when it's a command, and if it's a dot dot, when it's a command and it's a dot dot, what you do is that current equals to, you drop it, yeah, you drop it. Otherwise current equals to append current that. Okay, okay, so this is if it's a CD. Okay, I don't know. So you know, I need a break, and currently actually I'm thinking maybe actually we can rewrite this in more understandable way, because right now it's a bunch of if, nested if. So oh yeah, wait, we forgot, wait, this is a function, right? Okay, okay, line parts. Okay, so still good. Am I still good? Yeah, I'm still good. Current is a drop. If it's that, oh wait, current equals to, oh wait, what the fuck is this if structure now? So if that it's a command, okay, otherwise this part is, yeah, so this part is a command, okay. So if it's a command, what you do, so and if it's a command is cd, so if it's cd back up, so if it's cd, then you if it's cd, then if it's a cd, then depends on it's dot dot or not. Okay, so you actually don't want this line. Okay, so if it's dot dot, then drop current by 1. That's right. If it's not dot dot, then you append wait, this is repeated here. What the fuck? What? Oh yeah, we forgot. Shit. Yeah, that's why we had it twice, because we forgot to delete it. Yeah, because we were trying to modify the code to make it into this way, and we forgot to delete the old copy. Okay, so now it's better. So if it's dot dot, then current drop, otherwise current append, current yeah, append 2 actually, you can say yeah. So now let's do again. Select all, paste, run it. Now better. Let's see. Do we have, let's see, better. We don't have the repetition anymore. The repetition is just a editing mistake. Now, but we still have repeated path. You see? WinnieCusp, not sure if WolframLang is a good tool for this task. Seems to me a bit more complicated than it should. But the important is have fun and learn, isn't it? Yeah, well, I'm not sure I would agree with that statement. You know, this is not suitable for WolframLang. Yeah, but it's complicated, you know. It's getting, yeah, this doesn't look good. This fucking shit doesn't look good. But anyway, yeah, let's keep going. Okay, so where does this file name came from? So if the first part, you know, so if the line is not command, it means it's a size and file name. Oh, or the and file name. Okay. If the, ignore. If file, add to size lookup table. Okay. So if it's the, ignore. So, but if it's a file, the first part is not a the. So if it's a file, then we add the first part file size, the second part is file name, right? Yeah. Then the third part is a file size. So why is this file name? What is this? Append current file path. Append current file name. File path. Okay. So let's print this. Yeah, this is not. But it's. I think in other languages you're gonna get similar complexity. So file path. What is file path? Let's print. This is dummy's way of debugging. Why the fuck is that? Why does it just print file names? So file path. Oh, I see. Yeah, because the Wolfram language. Yeah, I know. When you use the with statement, this is like Lisp's let, but it doesn't. When you have the value, the later variables does not know the value of the previous variable. So over here, the file path will get a literal file name. So it's idiotic. So what you want to do is here's what you want to do. Okay, so just move this here. Okay, and move the variable here, or you can say this is xx3. Okay, so anyway, so let's just do it here. So so remove that, copy all, select all, paste, run it again. Variable file path is local variable. Shit. Now another problem is that because when you say this, then you cannot use width, because width is temporary constants. For each one of them, they must have a value. Okay, so let's change it to module then. Okay, copy all, select all, paste, run it. Fucking recursion depth. What? Recursion depth exceeded. Our code is wrong somewhere. What? Why is it recursion? Oh, because we forgot. Yeah, we forgot a semicolon. Okay, but let's move back this. Okay, let's just put that there and move this back here. Remove that semicolon and change this back to width constant. Okay, now select all, paste, eval. Okay, fantastic. Finally, we are seeing actual file names. Okay, file names, you see. So now let's see path, X path. Fantastic and beautiful. We're getting somewhere there, so we actually, this correct. There's a repeat. Is there repetition? No. Correct. Now the other thing to look up is size lookup table. Fantastic and beautiful. We're going somewhere. Next pinball, it says, I was searching for good keyboards and I ended up on your channel. Thank you. I'm glad I found you. Thank you. So today's live stream, so far it's been 3 hours, I think 3 hours and 16 minutes. We are solving day 7, and and so I spent 3 hours and it's not done yet, but very close. We're getting closer and closer. So far this is correct and this is correct. All we have to do now is to turn this list of file path into a tree, and we can do that by as we explained here, by just create a dictionary of key. Each of these key is just a directory name, each of the key is just directory name. Then we have a tree, the data structure of nested dictionary that represents the directory structure. Okay, so it's easy to do. So far so good. I think we are good. Close that. Don't save. Quit Wolfram language. Restart. So we have, we clear all the variables. And Wolfram language is, again, like I talked before, it's a Lisp system. So, and everything is a symbol. Now, one disadvantage of Lisp system, including Emacs Lisp and Common Lisp, is that after a while, you have a bunch of symbols. That's, you can clear them, but usually you don't do that. If you clear a symbol by mistake, you have a problem. So the point is that with Lisp system, including Wolfram language, oftentimes you just start over, like quit and restart. Actually that's true for Emacs Lisp as well. So in fact, for me, I quit every day. I quit and restart Emacs every day. Normally, if you just use Emacs, you don't have to. You can use Emacs for a month or more, which I used to do. Like you have 300, several hundred, or 1,000 open buffer, files. But if you actually start to code Emacs Lisp, then you have to restart every day, because you have to clear, all your local variables. You have to clear the symbol table basically. So that's one flaw with Lisp kind of system. You have a symbol table, and basically it's kind of like global. So all the symbols you ever used are stored there, even if it's some symbol you used by mistake. So what I'm saying is that if you are a Lisp coder, Emacs Lisp coder, you do have to restart almost every day. Okay, so far so good. So we have our code, and so here's the code, the full code. I'm gonna take a break. Okay, so here's the full code. Evaluate it, and we have built the basically that's a list of file path, and then we can build a tree from that. Now let's go to let's pop this back to today's talk show. So today's talk show. Now let's take the actual input and see what we get. Okay, the actual input, where is it? What? Where's the actual today's input? I thought I saved the file. What? Close that. Untitled. Close. Don't save. Close. Yeah. Oh shit. Okay, let's start a new window then. Okay, so now we go to talk show. We go to talk show, today's talk show. We drop to the directory advent of code 7. So here is the input, close, paste the input here. Okay, showing browser. There it is, today's input. Okay, now did I link this somewhere? Search for the current directory. Oh, so it appeared twice. Wait, it appeared only once. Okay, anyway, so copy the input, which is 1000 lines, and go back to Wolfram language. Let's see if that works. Okay, so you want the, so here is the proper input. Let's see what kind of things we get. Run it. Okay, so lots of directories and stuff, and let's go to the bottom. Okay, so it says 3000, 4000 items. Now let's see the path. Fantastic. So each one of these lists is a file path, and each subpart is a directory name. You can join them into a string if you want. So here is a file path. Let's join them into a string, okay? So we are making progress. Let's do that. Okay, so you want to map a function to each one of that, and the function will be string join. Okay, so map that function to the path, then each one of these is a string. Okay, huge. Then we say, go to the bottom, we say the last output and show them in column. Okay, oh, when you join the string you need to add a slash. Okay, so so when you join the string, you need to add a slash. Let's go back to our code, and XPath. Okay. You want to string join. Okay. Argument join by slash. Add a ampersand to make this a function. Okay. And slash add means map. This is a shorthand operator. So you are mapping this function to this path. Okay, so copy all, and we add semicolon here to suppress the output, suppress the long output. Okay, so semicolon, 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 semicolon. Okay, copy all, select all, paste, and let's open the input. Huge input. Okay, evaluate the code. Yeah, we still forgot somewhere. Why is it outputting the shit? Oh yeah, the last part. Yeah, that's what we want. That's, oh, what? Wait, did we do it correctly? No, I didn't do it correctly. What? Let's look up join string. String join. Let's look up string join. A list. So why is this not correct? So let's get the last item. So last item is that, let's try string join. Okay, the last output, and we want to join by a slash. What the fuck is that? What? Let's try it again. So XPath, let's get the last item, slash slash last. Last returns the last item. Slash slash is the postfix notation, like the Unix pipe. Okay, so then you do that. Let's see what oh, you wait, that's a mistake. Okay, so do that. Wait, what? So where is our slash? Let's try use some other character plus. Oh, you want to map to, not, that's right. And string join. Concatenation. Wait, how do you add an extra character in between? Okay, that's not string join. String rifle. Oh yeah, so you want to use string rifle instead. String rifle. Yeah, so string rifle, you want to map string rifle with that. Okay, let's do that. Now it's much better. You see, each one of these is a string. Yeah, okay, so we got, this looks correct. Is it, does it look correct? Yeah, let's use slash slash column. What? Yeah, what did I do? Yeah, select or delete. So paste again. Let's paste this. Paste that. Yeah, where's the fuck? Select all, paste, slash slash column, show them vertically. So this is correct. Oh, except we got double. Why is that double in the front? Anyway, so we got a list of paths. Now we need to turn this into a nested dictionary. That's easy. Well, easier said than done. To do this, maybe another 20 minutes. Okay, I'm tired. This video is already 3 hours and 30 minutes. Okay, I gotta get up and walk. Okay, so let's continue. Let's just do something. First of all, why do you have the double slash? Okay, let's go take the input. Let's not, 1000 lines. Let's not do that many. Okay, let's just search for CD. Let's truncate it. We want more input, but we don't want this many. Okay, so let's say up to here. Okay, so that's our input. Okay, now go back here. replace input by that, select all, paste, run it. Okay, that's more manageable. Okay, but now we got a problem of // where is the / came from? Because almost every one of them got a /. So let's search for /. Okay, then string rifle. So we don't actually contain any / anywhere. So why is it? Oh, okay. So because the Unix command, when you do the Unix command, you can just cd to the root multiple times. Right. So when you have that's a special case. So the reason is that, where is it? Where is our talk show page? So the reason that when you cd, normally cd your name, but when you cd a / that has a different semantic than name. Because normally the name is the current directory, the relative to the current directory. But when you have a /, that's an absolute, directory file path. So it's not simply a name, but so there's a special semantic attached to it. So we need to add that another special case here, you see. So if it's ... So if it's ... then do that. Otherwise you can just add another if statement, change this into another if statement. If. Okay, so this is inefficient because we are doing the XX third part multiple times. So anyway, so if it's a /, well, then it depends on whether / is the first time you encounter / or not. Fucking idiotic shit, Or we can just cheat, once we got this result, we just remove all double /. let's do that. Yeah, good point. Vin's that's kind of cheating, that's kind of cheating. So let's see, what is our XPath? How do you fix this? XPath. Oh, wait. No, wait, this is actually correct. It becomes incorrect when we join them. That's when the extra / shit, all our logic is like we are logically analyzing incorrect logic. Anyway, we are trying to give excuses to why we are wrong. But anyway, so this is correct. It's just that when we join one of them together, that's when the logic is wrong. When you join them together, you add a / in between, but you shouldn't do it in the beginning of the thing. And the reason for that is okay, so here actually, so this is interesting. So this indicates that the traditional Unix way is actually logically inconsistent. Because if we consider / is a root name of a directory, and / is also used as a directory separator. So when you have a root something, you really should begin with double slash. So yeah, so this problem shows that the traditional Unix way is actually logically inconsistent. The traditional Unix file path. Yeah. And what about Windows? I don't know. Let's not think about too much about other things. Anyway, so we got that. So we need to turn this into a association. Let's do that. I need to take a break though. Okay, so how do we add association? So go back to, we want to turn each of these lines into a nested association, and we can do that by just, let's look at my Wolfram language tutorial. Association. You need to turn this list of strings into a nested syntax for association. Okay, so association add key. Okay, so that syntax is actually easier. So, oh God. So essentially we want it to become, let's see, where's our code? XPath. Where's the tree? Where's our tree? Well, we don't have tree yet, so we need to, wait. The tree, okay? The tree is our tree. So what we need to add is that over here, we want to, we don't need that part. Copy, actually. So we want to turn this list of path into the tree. So each one of that is gonna be, each of the element is gonna be something like that. So again, we map a function to the list of path, and the association variable is just the tree, something like that. Okay. So you need a function here. So let's write out map so it's easier to understand. Okay, we don't care level 1, it's always level 1. So you want to map a function here. Let's write out the full function name. Okay, and you have a bunch of variables and the function body. So basically it needs to do something like that. Not easy. So each of the element will become the key. I'm going to for a rest. Good stream. Okay, we'll be back tomorrow. Thank you for watching. Bye. Yeah, I'm gonna take a break too. In fact, I think stop it. Yeah, yeah, let's stop it. So we didn't complete. We do it tomorrow then. 4 hours. Okay, yeah. So thank you guys for watching. Bye guys.